Okay, well, we'll see if I can do it capably or not, but Igor is very disappointed he was not able to make this meeting, and I'll try to do my best to do his talk justice. Okay, so the LEND instrument is a set of neutron detectors, as you well know. It's got a collection of 4 uncollimated detectors. These measure essentially the moon from limb to limb, very much like lunar prospector neutron detectors. The very important new addition to this, though, is the collimator. There's 4 detectors buried at the bottom of these long tubes, and these collimator tubes are designed to greatly increase the spatial resolution of the instrument, and that really helps a lot in terms of understanding what's going on with the neutrons. Essentially, the main objectives of this instrument are essentially global mapping of the lunar neutron flux in different energy ranges. It has very high spatial resolution due to these collimators. Gives us about 10 kilometer resolution at a 50 kilometer altitude. And we, of course, use that to map out polar hydrogen. The epithermal neutrons are a very strong indicator of hydrogen, and hydrogen may in some cases actually be indicating water ice, although we don't know that for sure. We'll also be looking at observation analysis of the permanently shadowed regions. As you'll see, the neutron depressions, i.e. the hydrogen enhancements, don't really correlate strongly with the permanently shadowed regions. That was kind of a surprise that came out of this investigation. I think it's really pretty important. In addition, the instrument also monitors solar activity. Looks like we got 2. Yeah. Okay, here's a 3 different maps in 3 different energy regions showing the moon. The thermal neutrons are up here, epithermals here, and the fast neutrons down in this map. If we go on to the next one, we can see in the thermal neutrons, and the thermal neutrons really do map out quite well the various landscape features that one can see in the moon. The epithermal neutrons show even some of the very small craters tend to show up in the epithermal neutrons. Mostly the epithermal neutrons are studied with respect to looking for hydrogen, but it also is very slightly sensitive to some other compositional effects as well. Here's a map of the north pole of the moon, where we're taking the LEND data with the omnidirectional, in other words, the uncollimated sensors, and comparing them to the data of the lunar prospector neutron spectrometer from their uncollimated detectors. Unfortunately, the color palettes aren't the same, but if you look carefully, you can see that the maps really are very, very similar. Essentially, the LEND omnidirectional neutron sensors are performing pretty much identically to the lunar prospector sensors. This is a similar comparison in the South Pole, and again, you can see that the this general big low trough that's found with a lunar prospector can also be seen with the omnidirectional LEND sensors. Here's another comparison between the data. This is just a latitudinal average going from the equator down to the South Pole, back across the equator down to the North Pole, and the data for the LEND collimated sensors, as well as the omnidirectional sensors, and the lunar prospector neutron spectrometer, all are showing very similar results with this well-known depletion in epithermal neutrons at the poles due to hydrogen. Okay, here's a map comparing the collimated with the uncollimated detectors. This is the LEND uncollimated, this is the LEND collimated. This is the North Pole. You can see some enhancements here in hydrogen or depletion in the epithermal neutrons. Unfortunately, I think the color palette of this makes this not quite as easy to see. In my talk, I'll be showing later some maps which has the same data, but just a little bit easier to see these enhancements. But nevertheless, they are there, and they are real with much greater spatial resolution than what you see with the uncollimated detectors. Same thing for the South Pole. Again, the uncollimated over here. Here with the collimated detectors, you can see a very strong enhancement of hydrogen, depletion of epithermal neutrons at Shoemaker. Over at Cabeus, these are both well known. We've outlined here some of the permanently shadowed regions. Here there's a very strong relationship between Shoemaker and the neutrons. Here with Howarth, there's no relationship whatsoever. There is no neutron enhancement. Cabeus, as is well known, does have a neutron depression. It corresponds to Cabeus, but it's also quite a bit bigger. I'll be getting a little bit more on that in a moment. Okay, here's where some of these various neutron suppression regions, NSRs as we call them, have been converted to the equivalent amount of water. So it's really hydrogen expressed as the equivalent amount of water if it were in the form of H2O. Homing in on a couple of the regions in the south, this is Shoemaker, which is the strongest of all of the neutron suppressed regions that we see. It's, you can calculate the uncertainty on this relative to a global average. It's down about over 8 sigma. If you compare it just to the local surrounding areas, it's still significant at 4.5 sigma. It's really a pretty big depression. On the next slide, we show how it correlates very strongly with the topography of Shoemaker as measured by Lola. You can see it follows this edge very closely. It doesn't have quite the suppression on the equator-facing slope. The poleward-facing slope looks like it has more hydrogen in it. And this is actually a conclusion that Tim McClanahan's been talking about. It's a pretty general observation that the poleward-facing slopes seem to have more hydrogen than the equatorward-facing slopes. Here's a comparison of the LEN data to the diviner temperature data, and you can see there's also a reasonably good correlation there as well. Cabeus is, of course, the one where L-Cross had its impact. The permanently shadowed area is here, but the neutron suppression region is quite a bit larger. If we compare it to the topography, we see that in this case, it doesn't really line up quite so well with the topography. On the other hand, it follows very well the temperature data from diviner. There's really some interesting things going on here that I think it's fair to say we don't understand. In other words, why is it that some of the PSRs have neutron suppression associated with them, some of them do not? Here it's following the temperature data nearly perfectly. It's not so well following the topography. I think there's a lot of interesting information going on here. I have to admit we don't quite understand it yet. Okay, so conclusions, LEN's providing a continuous global mapping of the lunar neutron flux. It's providing high spatial resolution observations using the collimated epithermal neutron detectors. As I mentioned, these observations show that the correlation between the hydrogen-rich areas and the permanently shadowed region is really not as straightforward as people had previously thought. Igor's paper in Science goes into that in a bit more detail. The neutron suppressed regions for Shoemaker and Cabeus we talked about. And I'll be going into a little advertisement for my talk in the afternoon. I'll be going into a little bit more details about the NSR and the spatial resolution of the instrument. But one thing that I would like to talk about, and I'll be emphasizing this more in my talk this afternoon. This instrument is really putting out exquisite quality data. There's a small fraction of the community that disagrees with that. There's unfortunately a bigger fraction of the community that doesn't know what to believe. This instrument's performing exceedingly well. Thank you.
Any questions for Bill? Oh, could you please give your name and affiliation?
Ballroom University. So if you compare the whole moon maps from the lane, correlated and omnidirectional detectors, they look qualitatively very different. Surely you should expect the map from the correlated detector to be a sharper version of the omnidirectional map. How do you explain this?
It really is not the way you described it. It's kind of an artifact of the color palettes, the way they're stretched. What is a very broad, continuous low comes out as all blue and purple when you're looking at the uncollimated detectors. We've got a bigger dynamic range with the collimated detectors, so when you put that on a color palette, there's only a very small fraction of the map that comes out blue and purple. But if you take the collimated data and smooth it out by averaging over very large areas, it ends up looking very much like the uncollimated data.
Oh,
So if you look at the Mare regions, you get a bump in the count rate from the correlated detector, and you get a dip in the count rate from the uncorrelated. So you can change the...
Oh, I'm sorry. I thought you were talking about in the polar regions. Okay, and when you're looking at the lower latitudes, what's going on there is the collimators are not completely opaque. The neutrons coming from the side will go through the walls of the collimator. The fast neutrons are more able to go through the walls of the collimator. And so in the lower latitudes, really the collimated data is not nearly as useful as the uncollimated, because you're essentially changing the ratio of fast neutrons to epithermal neutrons. So in the lower latitudes, you really want to be using just the uncollimated data. There's a background correction that we make, and again, I'll be talking about that in my talk this afternoon. Oh, I'm sorry, okay. The question had to do with the fact that the epithermal neutrons as detected by the collimated detector look different than the epithermal neutrons as detected with the broad uncollimated detectors. And the reason for that, as I mentioned, is the different sensitivities to the high energy neutrons.
we have
Why don't you come listen to my talk this afternoon? This is really beyond what this group needs to hear. I'm sorry? You want to see that slide again? Well, this is one, I guess. Here's the north and the south. Anything else?
any other questions for Bill? Well, yes.
In your closing statement, you said there's disagreement with between what a minority thinks and well, the data. In your opinion, what does the data say? Oh, in your closing statement, you said there's disagreement between what a small minority thinks. And in your opinion, what does the data say?
The data says that this instrument is performing That is to say that this instrument is performing fabulously, and the proof of the pudding is in the eating.